Okay. So first thing, I meant to mention this in lecture and I forgot. There was a link to in last week's week 5 overview. This said homework 5. I didn't hit publish on it because there's no points associated. It's basically just extra work. And so if you tried to click that link and follow to it, it gave you an error saying that this assignment's not published yet. That's because I didn't expect you to be doing that. But if you wanted more work, I can turn that on. You don't have to do it. It's totally optional. There's another assignment for this week. It's going to be more nomenclature practice. So nomenclature in chemistry is just how do we name stuff. So that's what we were working on today with the ionic compounds. If you want more practice, there's homework for week 6 and a key that's available, but you don't submit anything. There's no points associated with it. So it's just if you want more practice with this stuff we're going over. And the key is available, is posted as well. All right, so the other announcement here is that this packet, the molecule shapes with pH, PHET, this is next week's lab. But since I'm not going to see you on Monday, we printed it out for you ahead of time. You don't need the printed out version. You can do it all from your computer, but it does have you doing some drawings and things like that. So you might prefer it.
So we don't have to work for this week.
Not for this week. All right, so any logistics questions to go along with that stuff? Cool. All right. So we ended talking about covalent compounds in class and talking about those molecular compounds doing Lewis dot structures. When we name covalent compounds, it turns out with covalent compounds, chemistry has a whole series of different types of nomenclature, different ways we name stuff, depending on what that component is and where we find it. So like biology and biochemistry has their own way of naming compounds. Inorganic chemistry, which is what we're doing in this class mostly, has their own way of naming things. And even within inorganic chemistry, there's 3 different versions. So I'm going to teach you 3 different nomenclature systems for this class. The good news is I already taught you one. Ionic nomenclature, like we did in class, is just say the name of your cation, say the name of the anion. And you make the charges are always going to add up to 0. Covalent compounds are when you have more than one non-metal forming a compound. So things like NO2. NO2 is not an ionic compound because both of these, nitrogen and oxygen, are both non-metals. They're both to the right of our stair-step line, right? All of our non-metals are trying to gain electrons to become more stable. So we know that this is going to be a covalent compound, also called a molecular compound, because it's entirely made up of non-metals. And it turns out, though, there's multiple ways, unlike with ionic nomenclature. With ionic nomenclature, we don't have to specify how much of everything we have because the charges do that for us. With these covalent compounds, because they don't actually have charges, there's actually more than one way that you can have nitrogen and oxygen make a stable compound. You can have NO2, you can have NO3, you can have N2O, you can have N2O, N2O4, are all stable, well, relatively stable compounds. And we can draw Lewis dot structures for each of these. But the trick with that means that we can't just say nitrogen oxide when it comes to naming these, because we need to specify how many of each of these we have. So this is where we get into those numerical prefixes. They're all based on the Greek, mono, di, tri, tetra. But basically, we're just going to explicitly say how much of everything we have. So for this first one, we would just say, so let me write those. So 1 is mono, 2 is di, 3 tri. So most of these are common, right? 4 is a little bit different. It's not quad, because quad is actually Latin based. It's tetra is the Greek word for 4. 5 is penta. 6 is hexa. With the A or not? I'm mixing up my. It's either hex or hexos. I think it's just hex. Okay, then go with that. Sometimes we drop that A to make it make more sense when we don't say hexaoxide, it's hexoxide. So we don't double up the vowels usually. I'm not going to mark you down either way. As long as it has HEX, I don't care if you put the A in there. 7 is hept. 8. Known. And deca. Basically, you can go further than that, but we don't really see anything. Anything larger than 10 atoms is going to be named using probably an organic nomenclature, which is this whole other beast that you'll learn when you take organic chemistry. So basically, we just use these to specify how many things we have. So like for this bottom one, we say it's dinitrogen tetroxide. So we know it's nitrogen, and we know it's oxide. And then it's 2 nitrogens, so we say dinitrogen. And it's 4 oxides, so we say tetraoxide. So the full name for this compound is just literally say how much you have of everything. And you use the prefixes to say that. The only exception to that is that usually with these compounds, the first element you say, there's only one of them. If there's only one and it's the first element, we don't say mono for the first one. If you don't say a prefix, you assume it's mono. So this first one would be nitrogen dioxide. We don't put the mono in front of it if it's the first one. So to give you an example of one that does have mono involved would be CO. CO is a covalent compound because it's all nonmetals. So we just specify how much we have of everything. We don't put mono in front of carbon, so it's just carbon. And then we say, and again, this is one of those cases where sometimes the double vowels get dropped, so it doesn't look like monoxide. So we just say carbon monoxide. We just say one of the O's. Right, carbon monoxide is CO, is the formula. Carbon dioxide is CO2. Right? So this is a really simple naming system. You just have to know when to use it. In fact, ionic nomenclature was also pretty simple. You just had to know when to use it, right? So one of the trickiest things about nomenclature is to know which system you're supposed to be using. Right? So for covalent compounds, it's when you have all nonmetals, you're going to use these prefixes. If you have a metal and a nonmetal, then you're going to use the ionic nomenclature. We just say the name of each ion. All right, so questions on these?
The Lewis dot structure that only applies to non-metals then?
You can do Lewis dot structures for ionic compounds. I don't think it's very helpful because you basically take a metal that is missing all its valence electrons. So it looks like it has no valence. Usually you do a Lewis dot structure with no electrons around it then. And then you're putting it with something that has a full valence already. So it's not really a Lewis dot structure. So like for sodium chloride, it would just look like Na, and then chloride would look like this. It's not really a Lewis dot. So you can do that, and some textbooks teach covalent or ionic compounds, Lewis dot structures. I don't find it useful, so you'll never see it again. Nobody who takes more science classes will draw that Lewis dot structure. They will draw Lewis dot structures for stuff like this. All right. So that's all the intro you really need for these covalent nomenclature is you just have to know these and know when to use them. The next piece is basically going to add a tweak to ionic nomenclature. So ionic nomenclature is just say the name of the cation, say the name of the anion, which is simple enough as long as we're only using ions that are on the periodic table. The thing is that there's some covalent compounds that have a charge to them. So for instance, there's a stable compound that's NO3 with a negative charge. That's not the same as nitrogen trioxide. Nitrogen trioxide is neutral. This is a different thing. So this is what we call a polyatomic ion, which is a mouthful, but if you break down what that means, poly means more than one, atomic atoms. So it's an ion made of more than one atom. And all of our polyatomic ions make sense in the context of you need to fill all the valences and you need things to be stable and you need to be able to draw a Lewis dot structure for them. But the easiest way to get your feet under you when it comes to using these polyatomic ions is kind of to memorize their names. So this is going to be the next in-class quiz. Is this sheet right here. Polyatomic ion sheet. There's some amount of a system to it. It's not totally random how these names work, but it's random enough. And we care about the charges now that we're doing these ionic compounds. So if we need the charges, if we need to know the charges in order to figure out how many of each of them. Sorry, I have a kid at the doctor right now. So I'm trying to make sure I answer that in a minute. So we need, if this is going to be incorporated into our ionic nomenclature, we need to know the name of it and the charge that goes with it. So if you check your list of polyatomic ions, this is going to be what you're going to study from for the quiz. For the quiz, and we'll do it a week from Wednesday again. So next Wednesday, a little bit more memorizing. Sorry. This for next Wednesday. Okay, there are some tricks to it to help you. So you don't actually have to memorize all of them. If you learn some rules to go with it, you can also just make flashcards and just power through. The way that we'll do the test is I'm just going to give you this and I'm going to go through and randomly either delete the name or the formula. And you have to fill out the rest of it. No, so like I might erase ammonium and leave NH4+. And then on the next one, I might leave hydronium and erase the formula for all of them. It'll still only be worth 10 points. It's going to take a little bit of practice, but that's what this assignment is basically let's practice using these. And you're going to use this, you're going to consult this every time you do it at first. Then as you get more and more practice, you're not going to need to look at this as much. You're going to be able to remember, oh, nitrate, that's NO3 with a -1 charge. Right, so how that works for ionic compounds. It's just another type of ion. Remember, for ionic compounds, the way we name them is you just say the name of the cation, say the name of the anion. This is just another list of possibilities. Almost all of them are anions. There's a couple of cations at the beginning, hydronium and ammonium. But other than that, they're all negatively charged. They're all negatively charged. That means that you're still going to have like a metal and then something else with it when you're naming these things. So if I had something like Na+1 and nitrate with a -1, I can still write what the formula is going to be. Our rules don't change for ionic compounds. It's still, I want to take as many cations and as many anions as I need to add up to 0. So if it's a +1 and a -1, that's easy, right? Need one of each of them. So this formula would then be NaNO3. This whole thing has a -1 charge collectively. So it takes one nitrate and one sodium ion to make our formula here. And when we name this, we just say the name of each ion. Sodium nitrate. Right, so this is, it's not that big of a list. This is not an exhaustive list of polyatomics. These are just the most common ones that show up in this class. There's practically an infinite amount of polyatomic ions if you really get into it. These are the ones that show up most frequently in this class and on Earth. And you'll notice that they all end in one of two suffixes, three technically. They all end in either ate, or "ide." I'm going to do my best to over enunciate these so we don't mix up "ide" and "ite." I'm going to be very careful with that so that we don't mix up nitride, which would be N with a 3- charge, with nitrite, which would be NO2 with a -1 charge. Right, so those suffixes are going to wind up being important when we start talking about acids in a minute. But for now, when we're doing these ionic nomenclature, just refer to this. And the keys, and I'm going to say this again in lecture on Wednesday, so you'll hear it twice. But there's a connection between ates and ites. If you look at these, there's a bunch of different places. You've got nitrate and nitrite. You've got sulfate and sulfite. You've got phosphate and phosphite. All of those, if you memorize the ates, the ites are just the same formula, the same charge, missing an oxygen. So nitrate was an NO3 with a -1 charge. Nitrite is NO2 with a -1 charge. Phosphate is PO4 with a 3- charge. So phosphite is PO3 with a 3- charge. And that's still the way my mind breaks these down. The ates are, that's sort of like the base name because those are the most stable form. This form that you find these compounds in the most often. And so if you have the ates down, then you just have that rule in your head. If it's ite, I do the 8 and I take away an extra oxygen. Okay, so chlorate.
Except that I take away.
You have one fewer oxygen. This would be phosphate. This one would be phosphite. See, it's the exact same things if you're missing one oxygen. So if you can get the ates down, that actually has a bonus effect. If you get the ates memorized, then that gives you another 6 of them already that you have down. Right, that you don't need to spend as much time memorizing. So if I was choosing a way that I was going to study for this quiz, that's the way I would approach it. I would make sure I had all of the ates down really, really well, and then memorize the rules for adjusting that, for modifying. Right, and actually the complete version of that rule you actually see by looking at chlorates. So chlorate has 4 versions. There's chlorate, which is ClO3 with a -1. There's chlorite, ClO2 with a -1. if you continue that, you can actually take it further and get hypochlorite. Hypo means without, right? Like being hypoglycemic. Hypochlorite, you take away another oxygen, but still keep the same charge. What's the opposite of hypo? Hypo means without. What means when you have too much of something? Hyper. Perchlorate goes the opposite direction. Perchlorate, you take chlorate and you add an extra oxygen on it. So you get ClO4 with a -1 charge. This whole family of ions, if you know how the names work, you really only need to have this one memorized. Take chlorate, you turn it to chlorite by removing an oxygen. You turn it to hypochlorite by removing another oxygen. You go from chlorate to perchlorate by adding an extra oxygen. Right, so you don't need to have those rules down in order to do this assignment, but I want you thinking about them because it's going to help you when it comes to memorizing these for the quiz. Right, so when you start from chlorate and adjust it, chlorates are on here, right? Yeah, they are. Okay. Not all of them have that entire system. So like there's no such thing as hyposulfite. Actually, it's not common anyway. I think there might be a hyposulfite. There's definitely no persulfate though. So there's not, these rules don't apply to everything, but I'm not going to ask you about the ones that they don't apply to. Right, so I'm only going to ask you about the stuff on this list. All right, so one more practice. What would be the formula of calcium perchlorate? Calcium perchlorate. What's the charge on a calcium ion? +2, right? And perchlorate, ClO4 with a -1. So how many of each ion do I need? 2 perchlorates for every 1 calcium. So the way we write that is with parentheses. Okay, we don't distribute this 2 because this still looks like perchlorate to us, right? So we don't want to distribute it because Cl2O8 could be a totally different compound. So we don't distribute, we make it, we keep our polyatomics. If we have more than one polyatomic in a compound, we put it inside the parentheses and then we say 2 of this whole thing. We don't write it out like this. Okay. So little new wrinkle to ionic naming. And we did just learn ionic nomenclature today. So I know I'm throwing a lot of new material at you. It's nomenclature for this class is definitely one of those things that we want to kind of take our medicine all at once, get it done and get it down pat so we don't have to keep coming back and adding to it later. We're going to get it all done this week, keep practicing it. But then we're not going to, after this week, we're not going to learn any more new nomenclature for this class. When you take OChem, OChem's got this whole different can of worms, which also makes its own sort of sense, but it's very different than what we're doing here. And don't get me started on biochem. Those people just make up words all the time. All right. questions on polyatomics? Right, last piece that you need. And this is the last type. So far we have ionic nomenclature, which includes polyatomics. We have covalent nomenclature, which just uses these prefixes. The last type of nomenclature is like a subset of ionic nomenclature. Acids look a lot like ionic compounds, but where the cation, where the positive ion is a hydrogen. So they don't, so ionic nomenclature, we could look at it and say, okay, it's a metal and a non-metal, or a metal and a polyatomic. I know how to name that. If written, and it looks kind of like a polyatomic, or looks kind of like an ionic compound, but where your positive charge is a hydrogen, that's called an acid. We'll talk about properties of acid and stuff like pH in a couple weeks, but we're going to learn how to name them now while we're doing the rest of this nomenclature. And so when we name acids, it's just like ionic nomenclature where we're going to try and separate it out and figure out what the ions are. In this case, we look at this and say, oh, that's an H plus and a chlorate. The fact that it ends in 8 is going to tell us how to name this. Anytime you've got an acid that, so it's something that starts with an H but looks like an ionic compound. We're going to just say, okay, if that's 8, you drop the 8. So whatever it is, 8, you drop 8 and you turn it into ic. And then you say the word acid. So this is chlorate. So this compound is chloric acid. I don't know why they don't just say hydrogen chlorate, but you don't for acids. The other possible suffixes that we can have. We can have ates, and that includes perchlorates. We can have ites, like chlorite. Actually, I'm going to clear this off so that I can write all of the acid rules together. So 8 turns into ic acid. Ite. You do the same thing. You drop the ite, you say add OUS, us. So HClO2, that's chlorite. So when you add the hydrogen in front of it, you drop the ite and it becomes chlorous acid. What's the other suffix that we have on these negative ions? Ide. Those are the ones like straight off the periodic table, right? Like chlorine becomes chloride. It's HCl. That's hydrogen chloride. We drop the ide. We say hydroic acid. So hydrogen chloride becomes hydrochloric acid. Again, I'm not sure why we haven't adjusted acids to being a more uniform nomenclature system, but we haven't. We're stuck with this for now. Hopefully within our lifetime that will change and you will not worry about it at all because you'll be well out of chemistry by then and not have to think about it very much. For now, though, we have to learn this. Here first and then Alex.
polyatomic ion sheet. There's like hydrogen phosphate.
Yes. Good question. So hydrogen phosphate, there's a few polyatomic ions that have hydrogen as part of polyatomic ion. The difference between hydrogen phosphate, so HPO4 with a 2 minus, versus phosphoric acid, is that your acids have a charge of 0. So they look like an ionic compound. If they still have a charge, it's a polyatomic ion,
Okay.
and we don't name it as an acid. So there's a few others like hydrogen carbonate, hydrogen sulfate. There's 2 phosphates that have hydrogens attached to them, but they still have charges in those cases. For it to be an acid, you have to have enough hydrogens that the charge adds up to 0, just like an ionic compound. Right? Because each of our H's is a +1. Alex?
How would hydroxide be? Yeah, how would hydroxide?
That's a great question. What would hydroxide be if we stuck an H plus on it? What does it look like if we combine those 2 H's? So hydroxide, the acid form of hydroxide is actually water. So we don't have a specific name for it, but if we did plug a name in for it, the acid version of water, we could name it hydroxyic acid, or you could call it water. There's a few ways to memorize this, to help you memorize this. I've heard my ride has hydraulics. I ate something icky. Sprite is delicious. It's silly, but it works. The way that I memorized it when I was in high school was the simplest formulas had the most complicated name. And I had a really good friend in high school whose name was Titus. And when I was memorizing these, I just got it stuck in my head, itis. So I remember my friend Titus from high school every time I teach this unit because they go together. So now you too, every time you think about this, are going to think about my friend Titus. And then I remember 8 and ick are just the other ones. If I had the first 2 memorized, that was the last combination. Probably my ride has hydraulics and I ate something icky and Sprite is delicious, works better for most people. But there's options out there. And it's one of those things, we'll just keep practicing with it. All right, so the way that this assignment works. The first page is pretty straightforward. Because it says, these are ionic compounds. Write the name of each ion. These are formulas or names. Write the opposite. They're ionic compounds. These are covalent compounds. It's basically telling you to switch systems every section, right? The trickiest part about this is the second page. We're not going to do hydrates, so you can skip the hydrates section. The trickiest part about this is part 5. Because part 5 doesn't tell you what type of compound it is. So each of these individual systems isn't too bad on its own, right? The trick is knowing when to use each of them. When do I name it like it's an ionic compound versus when do I name it as an acid versus a covalent compound? That's what all of page 2 is about. It's really good practice. So how do we know if it's an ionic compound? A metal and a non-metal, which includes our polyatomics. We know it's covalent when it's all non-metals and it's neutral. Right? If it's all non-metals with a charge, it's a polyatomic ion. But if it's all non-metals and it's neutral, we do this. And then if it looks like an ionic compound, but the charge adds up to 0 with hydrogens, it's an acid. So if it looks like an ionic compound, like this still looks like phosphate, but got enough hydrogens to make it add up to 0, that makes it an acid. And that's when you're going to use these. And so it's a lot to keep track of.
You said the hydrogens are up to zero?
If you add enough hydrogens to an ion so that it adds up to a total charge of 0, it's an acid. We can name it as an acid. Obviously, things like
This shit's just.
water don't really count, but as long as you have this for now, and this is why we're going to get this, we're going to memorize this, is so that when we have a cart full of chemicals up here, nobody's going to be confusing the sulfates and the sulfites. Everybody knows what the formula is so that nobody's going to grab the wrong jar because they mixed up sulfate and sulfite, for instance. Now, I'm assuming that everybody's going to memorize it and get it perfectly. I know that's not actually how it's going to work. We're going to get most of these down, and we're going to keep practicing this and get better and better at it to where you don't have to think about it too much anymore. And then as soon as you're done with this class, you'll probably forget it all. And if you're taking Gen Chem, you'll relearn it next year with a couple extras. Okay, so the better you get these down now, the more it's going to help you later. Any other questions? All right. That's concludes our mini lecture for this part of the lab. All you're working on for this week's lab is this. The homework assignment that's worth 0 points that you're not going to turn in is just a bigger packet that looks like this. So if you just want more practice, go do that homework assignment, but it's not worth any points, right? And if you run into any questions with that assignment, I'm happy to help you with that one too. But this is all you're turning in. It's 3 pages of practice. Cool. Bianca.
For 6 on the covalent ones, for the ASI, should be added for iodide. Triiodide.
Is triiodide on your list or something?
It's number 6 on the list.
So for AS, I'm going to stop the recording because now we're getting into the nitty gritty.